Hi there. Today, or at least this video, we're going to start moving into functions of several variables. We're going to start by talking about different coordinate systems, and first up are cylindrical coordinates. So what motivates this? Well, if you remember, in 2 dimensions, we look at polar coordinates as a useful coordinate system for describing certain curves. And so now cylindrical coordinates, big surprise, are useful for dealing with problems involving cylinders, and spherical coordinates are of course useful for problems involving spheres or hemispheres, etc. So what are cylindrical coordinates, you might ask? And I'm awfully glad you asked. Well, in the cylindrical coordinate system, a point in space is represented by the ordered triple r theta z. R theta, these are just the polar coordinates of the point's projection on the xyz plane. So we've got the point's projection in the xy plane, and then z is just the usual z coordinate in the Cartesian coordinate system, and you can check out figure 2.89 of the text, which I of course have reproduced for your convenience here. So how do we convert between cylindrical and Cartesian coordinates? Well, we use our usual stuff. So we have for the polar coordinate system, we have x is equal to r cosine theta and y is equal to r sine theta. And in addition, we know that r squared is equal to x squared plus y squared. That's pretty easy to check. And finally, tangent of theta is equal to y over x. And z is z because it's the same for both coordinate systems. So let's look at what happens in terms of curves. So in the cylindrical coordinate system, if I have a surface of the form r equals c, well, if I was in polar coordinates, that would be a circle. In the cylindrical coordinates, that becomes a cylinder because z is not specified. And so these guys are vertical cylinders. So that means they're oriented vertically. Vertical cylinders of radius c. Surfaces of the form theta equals c, as you can see by the picture here, are half planes, and they're at an angle c from the x-axis, because if you'll recall, theta is measured from the positive x-axis. So these are half planes at an angle c from the positive x-axis. And surfaces of the form z equals c, as we described before, those are just planes parallel to the xy plane. And we, again, talked about this previously, right? Because the z coordinate's the same in Cartesian coordinates, there's no change when we go to cylindrical coordinates. So same as in Cartesian coordinates. And again, these pictures are from the textbook, figure 2.92. Let's do an example or two. So let's convert Cartesian coordinates for the point 4, -5, 2 into cylindrical coordinates. All right, so here we go. We have that x is equal to 4 and y is equal to -5. So we know that r squared is x squared plus y squared, which is 4 squared plus 5 squared, that's 25 and 16, which is 41. And since tangent of theta is -5 over 4, and we know that the point, we call it in the xy plane, if I were just looking at the xy plane, is in the 4th quadrant, Well, that tells us that theta is going to be the arctangent of -5/4 plus pi, which is approximately, according to my calculator, 2.24555. So we obtain the point. So r is the square root of 41. Theta is approximately 2.2455, and z is just z, which is 2. And that's all she wrote. Now, let's do one more example, or two more examples. What type of surface is r squared minus 4 cosine theta equals 14? All right, well, let's just plug and play. R squared is x squared plus y squared minus 4r cosine theta is just x equals 14. Okay, so that's what we have so far in Cartesian coordinates, but of course, to identify it, we need to complete the square on the x part, right? So we want to look at this as x squared minus 4x plus y squared equals 14, and we're going to complete the square. We reviewed this a little bit previously, but remember, we're going to plus and minus. What are we going to plus and minus? We take half the middle term, divide by 2, and square it, so that's just 4 and 4. So if we do that, we're going to get, and now I'm just going to add 4 to both sides. Just to finish the job. So at the end of the day, what do we get? Well, this part here, that's x plus 2 quantity squared plus y squared equals 18. And what is this? If you know, this is a cylinder. It's a cylinder centered on the vertical line through the point 2, sorry. That's an x minus 2 squared, I just realized. Through the point 2, 0, and parallel to the, with radius square root of 18 or 3 root 2. So that's what type of surface that is. Let's do one more example before we go to spherical coordinates, and I'll make that a separate video for your convenience. Hopefully your convenience. Let's convert the Cartesian equation below into one in cylindrical coordinates. So we're just going to plug in, okay, for x, we're going to plug in r cosine theta. Z stays z. And for y, we're going to plug in r sine theta. So we're going to get r cubed cosine cubed theta plus 2 times r squared times cosine squared theta minus 6z is equal to 4 minus 2 r squared times sine squared theta, or, you know, combining terms in the appropriate way, we get r cubed times cosine cubed theta plus 2 times r squared cosine squared theta plus 2 times r squared sine squared theta minus 6z is equal to 4. And that's all I'm going to say right now about cylindrical coordinates, but we will be using them about a week maybe, I think. All righty. That is all for that one. See you for spherical coordinates in the next recording.